Okay, so in the previous discussion, we've had built up a framework for connecting and incorporating local frame symmetry to simplify the measurements, polarization-dependent SHG microscopy measurements of oriented assemblies. The next step is to look at a couple of to illustrate how this whole thing plays out with some simple examples and common examples. And collagen is a pretty good one to start with because it's a really common system for SHG microscopy analysis. It's the most abundant protein in the body, and it's a bright generator of SHG. So if you're looking at tissues, it's an obvious first choice to look. So what are we going to be doing today? We're going to be considering the case. This is for, although I should point out that the exact same analysis we'll be describing works for both the local interface to a membrane, anything that is a uniaxial assembly, including the interface to a membrane or collagen along the fiber axis. Anything that is uniaxial in symmetry will be applicable to the analysis described in this section. And the goal is to try and recover the local frame tensor elements, and we're just going to consider, for simplicity initially, purely polarized laboratory frame observables. But what do I mean by purely polarized? I mean, not only is it a purely polarized state in the sense that there's no depolarization. I want purely vertical or purely horizontal light going in. How do I take measurements of the second harmonic generation intensity recorded under different vertical or horizontal polarization combinations and pull out information with respect to local structure and orientation of collagen? So what do we have to work with? We have previously our discussion that related the local frame symmetry elements, the local frame tensor elements based on symmetry, and there's only 4 of them, four unique elements in a system of uniaxial symmetry. And we had a nice matrix that we could connect those back to the Jones or laboratory frame observables, the tensor elements that are measured in the laboratory frame of the microscope. And this includes all of the degeneracies, all of the full 27 cohort of non-zero tensor elements produced from this set of 4 unique non-zero values. And again, if we're just going to consider, we're going to keep things really simple right now and initially consider collagen that is oriented within the field of view. And that would correspond to a tilt angle theta of 90, because the theta is defined relative to the optical axis. And if we go through our rotation matrices and multiply everything out, what we end up with is this matrix. And of course, we went through this previously, so I'll be brief on where this came from. And this matrix describes the connection between the local frame nonlinear optical response for a uniaxial assembly oriented within the field of view. So there's only the phi rotation angle connecting that to the laboratory frame, and the laboratory frame observables, expressed as this vectorized form of the Jones tensor. Okay, and we're going to worry about, and we're going to assume one more thing too, that we know phi. We know phi from something. And the most obvious way, that's actually the word something for those of you who didn't know, the most obvious way to know phi is to use image analysis. If you got a fiber, if we go back to this image, if you got a fiber, then you can have a pretty good estimate of phi just based on analysis of the image. And phi is defined relative to the horizontal axis, just to be clear. So that would be the orientation angle phi that we're describing in this analysis. And I'm just recopying this shorthand notation where we can use an alphabetical representation for the different cosine and sine terms that comprise this matrix connecting the local frame to the Jones frame. So if we consider measurements in the laboratory frame based on pure polarizations, then if I'm measuring the horizontally polarized second harmonic intensity produced with horizontally polarized incident light, that's really only probing exclusively the chi-HHH tensor element, where the first index indicates that this is the polarization state of the double light, and then the second 2 indices indicate the polarization state of the incident light. In this case, if the local frame tensor elements are all real valued, then the intensity is directly proportional to the squared, we know it's proportional to the squared magnitude of chi HHH, but if they're purely real value, then the square root of that intensity will be directly proportional to chi HHH. And we can repeat this for every polarization combination. So we can look at the intensity on the horizontal detector for both horizontal and vertical incident light. And then we can also include intensities on the vertical detector for horizontally and vertically polarized incident light. And that gives us 4 observables that essentially are related to, these 4 observables are the elements of this chi2 tensor element that are accessible. So if we exclude this one, and are only considering pure polarization components, we have those 4, and those 4 correspond to this set right here if we assume everything is purely real valued. So we only have 4 of them, so we have to do some reduction. We're going to remove this row, and we're going to remove this row. And because we're removing this tensor element, because everything is zero valued, we can also remove this row in that column. And what we're left with is a 4 by 3 matrix here that converts the two. And this is, if we actually just plug and chug in for all those alphabetical numbers, alphabetical numbers, impressive. At any rate, if we substitute in for A, B, C through I, then these are the explicit cosine and sine functions for the dependence on phi that connects the two matrices. The two vectors. So now we're in good shape, because what we have here is a vector of 4 elements and a vector of 3 elements, such that we have more observables than parameters, and we can potentially invert this to solve for the most probable values of these 3 tensor elements in the local frame. And that inversion is straightforward to do as well. And this is, again, from standard linear algebra techniques were described in a previous discussion. As long as you know phi, it's straightforward to do this. The other nice advantage of this of having an overdetermined measurement is that we can not only recover the parameters themselves in terms of the individual chi2 tensor elements, but we can also determine the variance in each of those values, and therefore the uncertainty. And that's determined just by treating this matrix here as alpha. If we define that matrix to be alpha, then the diagonal elements of alpha inverse multiplied by the variance of the fit recover the uncertainties in each of the individual parameters